Project 3.3.4 CHUMP RAM Mux Address Accumulator and Control. The foundation of the memory system is the 74LS189 RAM, a 16x4 static memory chip that provides temporary storage for variables, intermediate results, and program data. The RAM accepts 4-bit address from the address register and uses the control word to determine whether it should read or write. A low pulse on write enable captures the data present on the bus, while a high state replaces the stored value onto the bus during read cycles. To manage the data flow, the 74LS157 multiplexer acts as a programmable traffic controller. Each of its 4 slices selects between 2 different data sources based on the active high select signal. This allows the CHUMP to decide whether a bus should carry RAM data, accumulator data, intermediate values, or ALU results. By ensuring that only one module drives the bus at a time, the multiplexer prevents contention and keeps computation clean and predictable. Memory addressing is handled by the 74LS174 address register. This hex D-type latch captures the value on the data bus and holds it steady across 6 outputs. 4 of those outputs are from the address lines for the RAM. The register updates only on the rising clock edges when enabled by the control word, ensuring the addresses remain stable throughout each load or store instruction. The processing pipeline centers around the 74LS377 accumulator. The octal register stores the ALU output and becomes a source of future calculations. Its outputs feed directly back into the ALU 8 inputs, forming a closed computational loop. By enabling the accumulator only when required, the CHUMP cleanly sequences multi-step operations such as arithmetic, comparisons, and branching. Coordinating all these components is the control EEPROM, an AT28C16 that outputs the 8-bit control word for each processor state. Unlike the program EEPROM, which stores high-level machine instruction, the control EEPROM stores micro-instructions, signals that determine when to latch the accumulator, load addresses, write to RAM, select multiplexer inputs, or trigger ALU operations. Every clock cycle retrieves a new control word based on the processor state, instruction bits, and flags, allowing complex behaviors to be built from simple hardware. As for the code, this Chumpanese language code subtracts 2 from a value of 8 until the value reaches 0. After this code is burned onto the program EEPROM, the control EEPROM reads the current opcode from the program EEPROM and uses it as its address. The opcode determines which instruction to run. The 4 most significant bits are sent into the ALU select pins to choose the ALU operation. The next 2 bits control the ALU's mode and whether or not carry in is used. The final 2 bits enable or disable the accumulator and RAM. And at the same time, the 2 most significant opcode bits are ANDed together to decide the program counter should increment normally or follow a different path. This concludes Project 3.3.4 CHUMP, RAM, Multiplexer, Address Register, Accumulator, and Control EEPROM.